This is my homebrew 8-bit CPU. It consists of an ALU on the left, a register file in the middle, and then a simple program counter and instruction memory on the right. The CPU is getting pretty messy though, and there's wires going all over the place. And since the ALU is now more or less complete and the register file hasn't seen any big changes in quite a few episodes, and we also haven't really changed the program memory and how we read 16 bits out of the 8-bit memory that much. So I think it would be great if we could move most of these breadboards onto dedicated PCBs and then put those PCBs onto temporary backplanes, such that we have a pretty clean CPU build with the features the CPU currently has, and I can focus on building out new features. And now with the ALU complete, I would like to focus on the pipeline of the CPU and more of the control logic of how the CPU works. This includes decoding instructions, splitting the CPU up into functional units and dispatching instructions to these functional units, and then dealing with write-back and instructions that take multiple cycles to execute, and dealing with the data access hazards that come with that. To do that, we'll need quite a few additional breadboards, and it would be great if all the rest of the CPU would be on dedicated PCBs, such that only the current focus, the thing that I'm currently working on, is on a breadboard. And then once that is done and working, we'll just move that onto a PCB as well and add it to one of the backplanes. As a first step, let me draw up a rough plan of how the backplane could look like and how we could arrange the PCBs that we are going to build. First up, let me change the units to use the same spacing as the regular pin headers and the breadboards. That's 1/10 of an inch, 2.54 millimeters. We already have a PCB for the general purpose registers. And we have 7 of these registers currently arranged in a stack. And I do like this arrangement of the registers, so let's stick with that. We currently have a breadboard with a bunch of bar graph LEDs which show what the data is on the write data and the 3 read data ports. I think moving that to a PCB and having that be a fixed part of the register file is going to be very useful because you can actually see the data as it flows out of and into the register file. And I assume I can fit the LEDs and maybe a buffer chip in the same footprint as one of these register PCBs. So let me just copy one of these registers and let's declare that the port LEDs. And let me maybe put that at the top of the register stack. And then kind of related to the register file on the breadboards, we had a move buffer, which we used to copy a value from one of the read data ports to the write data port to implement load immediate and moves. And we also had this immediate buffer that allowed us to use a part of the instruction as an immediate value and use that as one of the operands. I think it would be nice to have that kind of functionality close to the registers here and maybe just add another PCB below this register stack that deals with moving values between registers and loading immediates. And one thing we need to consider is that today the ALU contains the flags register, but in the future when we might have multiple ALUs or multipliers or other units that can change or read the flags, it would be beneficial if the flags register was actually just yet another register that lived somewhere in the CPU, and then the ALU just happens to read and write that register. And that will also make it easier to deal with the flags in a superscalar or out of order setting, where they become just another register operand to any of the instructions. And I think this PCB with a move and immediate buffer would actually be a good spot to also put the flags register. And this PCB then becomes more like a collection of a few random tidbits that we need to put on a PCB. But I think that's fine. We'll only have one flags register and we only need one move and immediate buffer. So it kind of fits that we put that into one auxiliary PCB. I'm not entirely sure how much space we're going to need for this, so let's maybe make this PCB a little bit larger, and then once we have designed it, we can actually resize this sketch to fit it exactly. And this is about as tall as I would like to make these stacks of PCBs, otherwise it's going to be pretty difficult to fit everything into a camera frame. But we also have that program counter PCB. Let me sketch it out quickly. And now that the ALU is also complete, we'll want to move that to a PCB pretty soon as well. I have no idea how much space this will actually take up on a PCB, but I'd guess it's going to be roughly the size of the program counter. So let me duplicate the program counter and let's call one of those ALU, and that's going to be the ALU PCB. And then once we've designed that PCB, we can actually go back in here and change the sketch. And then finally, another thing that really hasn't changed in the past 20 episodes or so is that program memory and how we load data out of a program memory by double pumping it and a latch circuit. And so I think it would make sense to actually create a small PCB for the program memory where we can put that latch chip, maybe a bunch of LEDs that show what the value is that comes out of the program memory, and maybe add 1 or 2 more latches to prevent the signal toggling that we see in the middle of the clock cycles right now. I think that should fit a plain old flash chip. Let me actually sketch out how large the 32-pin flash chips are, just to make sure that they actually fit on this PCB. And these circuits on the breadboards, they are interconnected with a whole bunch of wires that go all over the place. But now, if we have these as PCBs, we can actually put the whole thing onto a backplane and we can move the entire wiring onto that backplane. This will make the signal connections a lot more reliable, and it will declutter it significantly and make it much easier to work with the CPU. So let me draw a box around this to represent the backplane. I think I want to make it 1 stud wider than the PCB, such that there is a nice frame around everything. And now one thing to consider as we build out the pipeline is that we're going to add more and more PCBs to this. For example, I'm pretty sure we'll quickly need a RAM chip to act as the memory for this CPU. And depending on how we do instruction decoding, we'll pretty quickly want to put the entire instruction decoder onto a PCB. And it would be great if we could iteratively upgrade this backplane to accept those new additional PCBs and actually keep the CPU build decluttered, such that the only things that are on a breadboard and have these loose wires are the current things that we're building out. And if I look at this here, I think the one thing that will change a lot is the stuff around the program counter, the program memory, and the instruction decoder. But everything on the left, the port LEDs, the registers, and the flags, and the move and immediate buffers, I'm pretty sure will stay the same for quite a long time. So I think it would make sense to actually split this backplane up into 2 backplanes. One for the register related things on the left, and one for the ALU and all the other kind of pipeline related things on the right. And then whenever we're done with a piece of the pipeline or 2 pieces of the pipeline and we create 1 or 2 new PCBs, we'll just respin the backplane of the right-hand side here and add those PCBs. And now the left and right half are actually 2 distinct PCBs, and we'll need to figure out how to establish a connection between the left and the right-hand side. And the only thing I can think of is to actually have pin headers here in between the backplanes that will allow the backplanes to be connected to each other. We'll use these pin headers to move the interesting signals between the 2 backplanes. Things like the data going in and out of the registers, the immediate data from the instruction, the flags, the clock power, and all that kind of jazz. First up, we probably need all the data ports off the register because the ALU wants to read at least read data port 1 and 2, and it wants to write to the register file, so that's 3 of the ports already. And then the program counter also wants to read the 3rd read data port for its absolute chumps. So we'll need all of the register data at least. And that already takes up a lot of space, especially thinking about what other signals we will have to move between the backplanes. So I think it would make sense to double these up and to have a 2-row pin header. And let me add a note what signals we're going to put on that pin header. We'll also need to be able to control the write and read addresses of the registers. Those are 4 bits and we need 1 per port. So that's 4 4-bit signals we need to exchange. And I think we can play the same game here. We can merge that into a 2-column header. And on top of that, every port also has an enable signal. Let me just add those to this pin header. We also have the flags that live on this PCB down here in the bottom left. Those were pulled out of the ALU. So we also need a write and read data port for the flags. The flags are 4 bits each, so that's 2 4-bit signals that we need to carry between the backplanes. And then we also need to be able to control when the flags should update. So there's going to be a write enable for the flags. And the move buffer in here also has an output enable that we need to be able to control. And the immediate buffer here also has an output enable. And then finally, I think we also need the actual immediate itself that we want to potentially drive onto the backplane here. That used to be connected directly to the top 8 bits of the instruction. And I think we want to do the same thing with the backplanes, so that immediate has to cross between the backplanes somehow. Let me move the labels here to the right such that we can move the two backplanes closer together again. And then I think the neat thing is that when we have these two backplanes assembled, we can create a third small PCB that will just contain the connections between the backplanes, and we can use that to stitch the two sides of the CPU together. And these connections will probably stay more or less the same even across multiple revisions of the right-hand side backplane. So we'll just reuse whatever we have, and we'll make the right-hand side backplane grow towards the bottom and add more PCBs. Now, another thing that needs to cross between the two backplanes is power, so that's VDD and ground, but also the clock and the reset signal. And I think the easiest thing to do is to just put those signals onto a separate 4-pin header. And I think since power, ground, clock, and reset are such an essential connection, let's actually create a few more of those, maybe down here at the end of the stack of pin headers, and then maybe all the way down in the corner. Because as this right-hand side grows, it might actually eventually match the size of the left-hand side backplane, and then we'll have another connection point for good power and ground connection. And then for the sake of symmetry, we might want to have the same pin header connections on the other side of the backplanes, because right now I have no idea how exactly the CPU layout is going to look like in the future, and whether we want to be able to actually grow the CPU towards the left of the register file as well. Or we might want to attach more things on the right of this right-hand side backplane. So even if we don't populate the actual pin headers on the backplane, it would still be good to allocate some space for them and have the actual footprints on the PCB such that we could add them if needed. Alright, that looks like a pretty neat layout. And this will actually move most of the CPU off of breadboards onto a dedicated PCB on a dedicated backplane. And this will free up a lot of space on my desk and also free up a lot of the breadboards to go and build new fancy things. And over the course of the next few episodes, I want to build out these PCBs and the backplanes and actually migrate the entire CPU build off of the breadboards. And for today, let's start out simple. Let's go and build this port LED PCB up here. I've already opened up the general purpose register schematic and the PCB layout because the port LEDs will roughly follow the same shape, and especially they need to have the same pinout at the bottom. So let me create a new project for the GPR port LEDs. I think the port LEDs will want to inherit all these pin headers at the bottom here and basically have the exact same layout. So in the schematic, let me copy over those pin headers. And I don't think we need that big decoupling capacitor here. And we actually also don't need the clock. And now we could theoretically hook up the LEDs directly to the read data or write data ports. But the thing I don't like about that is that the LEDs take quite a bit of current to drive, so it puts quite a bit of strain on the buffers that drive the data out of each of the registers. And so instead of attaching the LEDs directly to the read and write data ports, I think I'll use a buffer chip in between to decouple the LEDs from the actual bus. And the buffer chip will basically act as an LED driver. And so the data we see on the ports, we're going to feed into the input side of the buffer. And then the outputs of the buffers will hook up to actual LEDs. Then let me wire up power and ground for the buffers, and let me tie the output enables to ground such that the outputs are always enabled. And then each of the buffers should probably have a decoupling capacitor. And I think we're actually almost done here. Let me copy over some of the logos from the general purpose register PCB. And I think that's about all we need. Let me run the rule check to see if we have any missing connections. Seems to be working. So let's switch over to the layout editor and actually build up this PCB. First up, let me arrange the pin headers so they match the general purpose register PCBs. And now let me arrange the buffers and the LEDs and the resistor networks. As a next step, let me arrange the LEDs. And let me start routing this up. Okay, that's pretty good. That's the LEDs laid out and wired up, and all the buffers and resistor networks also wired up. Let me distribute the capacitors throughout the PCB and make sure that everything else is wired up properly. Let me check which nets still need to be routed. Looks like just the power connections need to be routed. So let's pour some copper and let's create a VDD plane at the top and a ground plane at the bottom. Okay, let me add a few labels to the LEDs so it's easier to tell which port they belong to. And for stability, I think it would be good to have a few spots up here where we can solder in a few pin headers that will just sit on the back plane and prevent this whole PCB from sagging. Alright, I think that's it. Let's take a look at this in 3D. That looks pretty cool. This will be a great first addition to this registered file backplane that we're building. Let me order this up and then let's go and assemble this PCB. I received this back in the mail today, together with the solder paste stencil. Let's apply some solder paste to it. solder paste looks good, a little bit too much in some places, but I think it'll work out. Let me populate the components, and I'm going to start with the capacitors. Next up, the resistor networks. Pretty nice. Let me continue with the LEDs at the top. And last but not least, let me add the buffer chips. Let me turn on the hot air gun and solder this up. Alright, there was a little bit too much solder paste at the top with the LEDs. They were swimming around a bit, but I think it doesn't look too bad. Let me take a closer look at the solder joints with the microscope. And last but not least, let me solder the pin headers at the bottom here and the structural support headers up here. That looks pretty good. Let me give this a quick cleanup off camera and then we'll give it a try. Let me mount this to the breadboard such that we have easier access to the pins. Let me connect the power and ideally we'll see the LEDs flicker on and off randomly because there's nothing connected to the input pins, and so the buffers here will pick up some random noise and display that on the LEDs. Most of the LEDs turn on and then slowly turn off as the gate charges here at the inputs and dissipate. To make this less random, let me add a few resistor arrays to pull the inputs down to 0. Now let's test each and every single one of them. Wait, I think I've got a better idea. Pretty sweet, they all seem to work. Alright, this is pretty cool. So this is the next PCB that we're going to add to the CPU build. It's going to sit above all the other general purpose registers to show us what the input and output values are that flow in and out of the register file. In the next episode, I think I want to take a look at the move and immediate buffer and the flags in the ALU and see how we can put those on a PCB that's going to sit below all the registers. And after that, we can draw up a backplane PCB that can hold these two new PCBs that we've built here, plus all the general purpose register PCBs. And that's going to make for a pretty nice and compact core piece of the CPU. Thanks a lot for watching, like and subscribe if you want to see more of this, and see you next time.